order to determine the apparent location and size of a source, we use the PSL Profiler. The PSL Profiler should be connected to a computer by USB. We access the PSL Profiler through the PSL Wizard. It is merely a step in the procedure. We double-click in PSL Wizard to launch the program. We must initially hit New to select a new configuration. We will just simply save this as test. This will allow us to proceed through to the point, hit next. We need not fill anything in except in the source information page we must select the source type, for now Node.js, and now we can access the profiler using the Run button. This will launch the profiler page, which shows a live view of the CMOS camera and has a variety of other features. In the first instance and on the first time of use, we should perform a dark measurement to account for the pixels which are defective on the CMOS camera. We need only hit the dark measurement button, and we're prompted to move the filter wheel to the close position. We do so by rotating the filter wheel entirely down to the bottommost position, in which case no ND filter is in place. The CMOS camera is effectively blocked, and we hit OK. We can see on the screen a number of dark pixels. These will be saved and not used in the calculation, and we can hit OK. We need not repeat that measurement at any frequent occasions at all. We are now ready to use the PSL Profiler. The PSL Profiler is based on a two-lens system to image the source under test onto a CMOS camera for the determination of both the angular source subtents and the apparent source location. The first lens is fixed, the second lens is translatable and can be moved using a screw to the rear of the PSL Profiler. The PSL Profiler has at the entrance an iris diaphragm, which can be used to close or to open effectively the size of the lens. But the use of this should be restricted to only the most extreme cases. The reason being that in closing this iris diaphragm, one increases the depth of field, so everything appears in focus. Since the principle of the PSL Profiler is to determine where is the source in focus, where is the apparent source located, this is no use. So one should always ensure that we wind the iris diaphragm to the upper position, the open position. When a light source is switched on, a lot of light will reach the CMOS camera. And for this reason, to the rear, from this view of the PSL Profiler, is provided an ND filter wheel. This filter wheel has in position 1 no filter, so one can see the source under test. And having illuminated the source, we insert filters in index positions, ND3, ND4, ND5, and then ND6. Then we have a closed position. This closed position is used for the purposes of measuring the dark pixels of the camera. It is a one-off procedure effectively. So the profiler is located on a rail which is simply screwed down to the optical bench, and the profiler can run along this rail. The principle is that we initially locate the position of 100, so using the front edge to locate the position 100 on the rail, and set the PSL Profiler to that position. Now, the PSL Profiler has been designed so that it has a good resolution over the 1.7 to 100 milliradians field of view, which are considered by IEC and EN 62471. Its minimum measurement distance intentional was 200 millimeters, but can be used down to 100 millimeters where that is required. For this purposes here, we will use 200 millimeters. Having set the position of the PSL Profiler to 100 millimeters on the rail, and one can use an alignment aid. Here I have simply a business card on a set square, and one can measure the distance of 200 millimeters from the alignment aid to the front face of the PSL Profiler. If I open the ND filter wheel, I will have a view with no attenuation of the card illuminated by background lighting. I can adjust the position of the second lens to obtain a focus, and it will be shown in a subsequent software video how this obtains, and we can see here a good focus of the business card. So we can say the PSL Profiler is now focused on a position 200 millimeters distant. The principle is that we would then position the source under test at the same plane, and then illuminate the source. Now, there are two things to note. Firstly, clearly the CMOS camera will be in overload because of the light entering to the PSL Profiler. And secondly, it will be out of focus. And that is to say that the source will not be focused. We should no longer touch the second lens adjustment, but to get the source in focus, we should move the profiler on the optical rail. Firstly, we will increase the ND filter attenuation to get the camera out of saturation. And when the camera is more or less desaturated, indicated by the software by a green light next to the desaturate button, we can adjust the position of the profiler in order to get the source into focus. In this case here, I have a light source which has both a floodlight and spotlight view, which is an excellent demonstration of the use of the PSL Profiler for the determination of source subtents. Presently, we see a now saturated, but an image of the source on the PSL Profiler window. One can adjust the focus to have a visually good focus of the source, and one can apply the procedures within the software, which we'll look at a software demonstration to determine the angular subtents of the source and the source location. The apparent source location being the difference of the position of the PSL Profiler from its initial point at 100 millimeters to its present point. In the case of this LED torch here, in the floodlight view, then we find that the lens is in front of the torch is quite far from the LED, and the apparent source is located relatively near to the physical LED. And as one moves to the spotlight mode, we're using the lens to collimate the output of the LED. Then the lens is made to be closer to the LED, and we find that the apparent source location is very far away. Indeed, in the extreme case, behind the torch itself. We will now look at this through the software simulation to look at the calculations. Now we will repeat the entire procedure using software simulation to demonstrate the operation of the PSL Profiler. I have positioned the PSL Profiler to 100 millimeters on the optical rail. I have measured out 200 millimeters from the front face, and at that location position my alignment aid. In order to view the alignment aid illuminated by the ambient lighting, I will turn the filter wheel to the topmost position, to the open location, and I will desaturate, since the camera in this case was not in an optimal situation. We can see that the image is out of focus, and we can adjust the focus by adjusting the position of the second lens of the PSL Profiler. We can do so by rotating the rear thumbscrew. Rotating clockwise results in the imaging of a plane further from the PSL Profiler, and vice versa. So I will adjust the position to get the alignment aid into focus, which we have here done. So now the PSL Profiler is imaging a plane 200mm distance, and in the remainder of the procedure we should not touch the thumbscrew to adjust the position of the lens, and merely use the movement of the PSL Profiler to determine the distance from the reference point of the source to the apparent source where required. So at the 200mm position, I will put the reference point of my source under test. So here I'm looking at a torch, and I've placed the front plane of the torch at that reference plane. And clearly we're trying to evaluate retinal hazards. The eye would not see, in the worst case, the front plane of the torch, but the source. And we intend now to determine the location of the source. Please note that the aspect ratio is merely a result of the display properties and has no impact in the calculation following this procedure. We can then power on the light source, and the first thing we have is saturation of the CMOS camera, and we can rectify that by turning the ND filter wheel downwards into increasing optical density. Perhaps we can go one step back and try to desaturate. Whether this will succeed or not, we will see. If the signal level is still too high, the software will prompt us. We can determine the signal level by the RGB bars, and also by the light next to the desaturate button. Green, the signal level is okay. Red, overload. So we have desaturated successfully. Now we will see that the source is out of focus. So we move the PSL Profiler forward on the optical rail to get the source into focus. The focus is done by eye, and we can see here the wire bond on the LED chip and the electronic grid. So we are now in focus. Before proceeding with the calculation, we need to ensure that we are not saturated, so we will hit the desaturate button to obtain the suitable conditions for the operation of the camera. And once this is finished, we will fill in some of the required pieces of information. Now that the camera has desaturated, we can input the dimensions information required. The reference distance is the position, the plane at which the PSL Profiler is focused. So we set it up to image a plane 200mm distant. From is a name for the reference point of the source, so that following these measurements you can go through the measurement procedure and always use the same reference point. So for example, I will put the front face. The reference reading was the initial position of the PSL Profiler on the optical rail, which was 100mm. The source reading I will read off, and I see 75mm. In essence, we have moved the PSL Profiler 25mm closer to the source, and therefore the apparent source location is 25mm behind the front face of the source. And indeed, the physical chip I would estimate to be some 15mm behind the source. So we see we have a somewhat magnified image of the LED chip. With this information, we can hit calculate dimensions, and a Hull algorithm will look within the full image for the maximum signal, calculate 50% of that, and this blue band will come in from all angles to fit around the image, the maximum dimensions at 50%. And finally, 2 orthogonal dimensions will be taken, which are reported here as 3.01 and 2.97 millimeters. If you want to restart to make some adjustments, we can hit the restart button and go through the procedure again. When one has finished, one can simply hit the finish button and proceed through the use of the PSL Profiler. It's worthy to note that, for example, if we select the actinic UV hazard and go next, rather than tell us to do measurements at the required 200 millimeters for a non-GLS source, we have information from the PSL Profiler transferred 170 millimeters from the front face. Now we can go through the procedure of the PSL Profiler, which will be given in detail in another video, but it's worth noting here that going next and, for example, selecting the UV hazard, we will see that rather than being prompted to do measurements at the non-GLS 200 millimeters distance, information is transferred from the PSL Profiler, and here we see the measurement distance is 175 millimeters from the front face of the source. So we have this transfer of information and transfer of the named reference point to aid the user in performing measurements.